Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 472 longest balance Subarray 2. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this one. Apparently this one, not many people got it correctly during the contest. And yeah, it's a relatively difficult problem. I'm gonna go over the way that I solved it. There were a couple of silly mistakes, but actually I think my idea was kind of okay, right? Yeah, the idea here is, well, or I struggle a lot with this one. Obviously it's a Q4. I end up spending about 50 minutes on this one. N is 10 to the fifth. The number of numbers is 10 to the fifth. So they're both big things that we cannot take advantage of. And it does remind me a little bit of the problem that we did on the daily. The K distinct characters one or whatever. You could change a character from a little bit ago. I couldn't shake that for a little while, but that one, the solution is taking advantage that it only has 26 characters, which means that you're able to do bit mask things on it. I'm not gonna go over that solution obviously in this video, but that's not the right approach. So okay, so the first thing I wanted to notice, the first thing that I was playing with the idea is, like the key difficult part about this is the distinct part, right? Distinct odd and distinct even. I try to think about, okay, well, if there's no distinct, well, what is it, right? Well, if there's no distinct, then this is actually a very standard Leetcode problem. And I think I even talked about it either last week or something like this, very recently, about that same problem. And actually, I think it was like there's another variation of this where it's Q3, where we have two letters or two numbers or two letters or whatever, A, B, and you try to find like the longest in which they're balanced, right? So stuff like that. So that problem shows up in all the places. And that's the first thing that I was trying to think about how to do. I definitely played around with a lot of ideas with sliding window. I thought about binary search. If you watch the live portion, I even mentioned it, but I didn't think it makes sense because you can have an answer that has a length, I don't know, 6 but not 7 or something like that, or the other way around, or 7 but not 8, or like it's not continuous, right? So that I ruled that out pretty quickly. Sliding window, I was trying to figure out, okay, well, if this number, like there's hard to do sliding window without a fixed length, right? And I thought about maybe playing around with the length, but other than binary search, everything is n square, which is not good, right? And then I also played around with, I guess, this idea of contribution, which we're not going to go over too deeply because it's not the right way. But I was like, okay, well, if this character is the last character, or this number is the last number in a subarray, what is its contribution? And it's not actually the right answer, but it actually did lead me to the right idea. Okay. And what I mean by that is, okay, the examples are kind of weak. So that's why I was looking for an example to kind of draw. But basically the idea, for now, let's not worry about complexity, right? And we just try to figure out how to do it. And that's basically how I was trying to do it during the contest, actually, was just try to figure out if there's a way I can solve it first, another alternate way, obviously, other than the naive solution, right? But yeah, and this is a very common thing that I do for these subarray type problems, where I go, okay, well, if this is the last character, what is the answer, right? And I keep coming back to the two balanced things problem, right? Like because in this problem, the only thing that matters is odd and even and distinct, right? So for a second, I was like, okay, well, what if there's no distinct? Then now everything is just odd or even, right? Odd, even, odd, even, odd, even, odd, right? So something like that. And of course, in this way, the standard idea is going to be, just choose one. Odd maybe could be -1, and then even is +1, -1 +1, plus 1, right? And then the idea here is that to get balanced means balance means that when you do a sum of a subarray, there's 0, right? And as a result of that, I know I'm going a little bit fast because this idea keeps on coming up, so I'm a little bit lazy to keep on explaining it. Definitely practice a lot of problems, I suppose. But yeah, but the idea here is that, well, 0, that means that, and you could get that from a prefix sum, right? Because if you're trying to find some subarray where there's a 0, 0, then this subarray is just going to be equal to the entire prefix sum. Let's say this is the last character that we're talking about, minus some small thing. And because of this subtraction, let's just call this A, call this B. A minus B is equal to 0, right? That's what we want for the prefix sum. But that basically means if you kind of, do very simple math, A is equal to B, and because we're trying to optimize for the length, it also, because there are maybe multiple things that could be equal to B, if we're trying to maximize for the length, we're trying to basically say the first instance of B, because then now that maximizes the length, right? I'm going a little bit fast, but this is basic stuff that you just need to know. And this is, of course, the variation of problem where we don't care about distinct, just odd and even things, right? And I'm going probably a little bit fast, my apologies. But yeah, but then the question is, okay, now, however, we have to think about distinctiveness, right? Like, this is very well solved. We have, I don't know why, but we have a problem like every other month on it or something, as a Q2 or maybe even Q3, a harder variation like we did last week, right? So, you have to know how to do this. But the problem is that now we have to deal with distinctiveness, right? So honestly, for me, it is just about honestly, for me, when I was doing this, it took me a little bit of time to kind of validate the concept. But for me, it is just about, well, there are two things, right? One is that you have to try to think about invariance, meaning that only things change that you have to keep changing. So you don't have to change the global state all the time, right? What I mean by that is that, maybe there's this 2, and then we go, oh, we look back, there's 1, 2 here, and then there's 1, 2 here. So then we have to do some updates to those 2. Maybe, but another way of thinking about it is that, okay, well, but another way to think about it is that, let me just change the color, right? So we said that we have this 2, that requires an update to this 2 and this 2. But, and then you do some calculation or math or whatever, right? But the idea here is that, well, do we though? Because before that, we do here, and presumably we do an update to this 2 previously, so then now we don't have to update here because we already updated. So that's part of the invariant that I'm thinking about. And then once I do that, then I'm like, well, you only need to keep track of the last 2 then, right? And in a simple way here, because we assume that everything to the left, any other 2s to the left of this is already been updated, right, by this 2's update. So here, when we're at this 2, we go, okay, well, we have a +1, right? So then we want to convert this +1 to 0 because it doesn't have a contribution anymore because it's a duplicate, right? I mean, I was also thinking in both ways, just to be clear. I thought this way is a little bit cleaner. I thought maybe I could also convert this one to 0, but the short idea is still the same, which is that you have to convert one of them to 0. I think converting this one to 0 is a little bit easier. Maybe you could do it the other way. I don't know if you can, but this is the way I did it because then now I'm able to get some prefix sum inside, maybe, right? And that's basically the core idea behind this problem, right? The tricky thing, of course, is this is still a little bit hard, right? Because I mean, we can keep track of this index. That's all of 1. We have a lookup table. That's easy. We can do this update in pretty quickly. But how do you update the prefix sum, right? So so with this, I immediately thought about a prefix, a segment tree, right? To store the prefix sum. Because yeah, because then now, and this is what I mean. Normally, you would use an array and a lookup table or something like that to find the first index, and there's a couple of components there that we'll have to talk about because this is what also makes it even tough. And as you can see, this is, the no element is going to be equal to 0, then -1, back to 0, -1, back to 0, +1 actually, back to 0, +1, back to 0, right? So that's the number line. I kind of actually went outside the box, but okay, you get the idea. Oops. So this is the prefix sum, right? Okay. And this is the prefix sum assuming that we still have the +1. So then now, when we want to remove this +1, we're basically essentially subtracting 1. What does that mean? That means that now we want to alter this to -1. But this also impacts all the numbers afterwards, right? I mean, yeah. Short answer is yes, at least up to until this number, because then now this we want to contribute. So then now this, so then now you -1 on this range. You -1 on this range up to the prefix, right? And that's basically the core idea. So you do a -1 operation on all of it, or maybe I write it here instead. So then now 0, -1. And that's it, right? And also I this is a little bit wrong because I forgot to actually edit this one as part of this update. So technically you would actually update this to -1 first, and this change to -2, and then now this would have a -1, which then now we change to -2. Okay, fine. So I messed up a little bit on explaining, but ignoring the prefix for now, then you see what I'm trying to do. And for a segment tree, this is very easy operation. I mean, easy assuming you know segment tree, of course. But this is just the key. Sorry, I'm having a little bit of allergy reaction on my teeth or something. But the key idea, of course, and if you want to Google it, because I'm not going to go over it too deeply, is you want a segment tree with lazy propagation, right? And that's basically the idea, is that you could do a range add to these things, and you could kind of maintain this thing. And if you watch the live portion, you'll see me just to make sure that I get this state correctly before I do the next thing, because there is a next thing. And the next thing is, well, now that you do all these updates, right? How do you go back and solve for the thing where, okay, you want to find some sub thing is equal to 0. So then now you're trying to find, this prefix where this is equal to, I said b before, right? So then now, how do you search for this target, right? Inside the prefix. Because obviously, if you do a linear scan, that is O of n. You do it for every number, that's n squared. That's still no good. So we have to be able to find the first instance in faster than n time, right? And the key idea, and this part I will go over a little bit of segment tree, right? But before I do that, actually, the one thing to note is that all these numbers are -1, 0, and +1, right? Right? And what this means, and what's important about this, is that I don't know why my mouse is doing a little bit weird. What's important about this is that means that if you look at it in terms of a line, this is a graph. You start from 0, you go +1, +0, +1, -1, -1, -1, right? And the key part about noting this, right, is man, let me know in the comments if I'm wrong, because it's been a while since calculus. and I do this live. Maybe I should prepare a little bit more. That's another story. But the key thing to make an observation about this line is the discrete version of the intermediate value theorem, right? Because this is continuous and we're going plus 1 minus 1. Then now, if you look at the min and then the max, right? Let me change the color. Why did I even? Let's say that's the min, that's the max, that's the range, right? If you're given a range, every number in the middle appears, right? Because we're only, I hope I don't have to do a tough proof about this, but because we're only plus 1 minus 1, if we're given a range, every number shows up. And this is critical because then now we are able to find the number in log n time by walking the tree. All right, I'm gonna go a little bit about segment tree real quick. There's a lot of stuff about segment tree, right? To be honest, so I don't want to go that deeply into it because it is gonna be like a 4-hour video. I mean, it's already long, but so. But the key thing to note about segment tree is that okay, you have these nodes. So this one will go 1 to n, right? And then you have nodes on the left, nodes on the right. So left would be 1 to n over 2. I don't know why I wrote it this way. Dot 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 n over 2, and then this is n over 2 plus 1 dot 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 n, right? And so forth, right? Hopefully I don't have to explain the recursive part. I mean, you really should know a little bit about segment tree if you want to solve this problem. For me, honestly, and I always say this, you probably don't need to know segment tree for interviews, unless you're in India. But you want to solve these problems and it is what you want to focus on, then it is what it is, right? But then the key idea here then now, right, is that we have all these nodes that represents region inside the segments, right? And then the key thing to note is though that now all we have to do to find the first instance is just to keep a range, and that's it, right? Because here we can say we keep a range on the min and the max, right? And let's say here we keep the region and the min and the max, and then let's say we have a target number. If it's inside, then we're good, right? So t, right, for some target. If it's outside, that means that it is not found, right? Hopefully that makes sense because of what we just did with the intermediate value theorem. Okay, and then now we call what we're trying to do. We're trying to get the first instance of it. So, and because we know that, I mean, if it's not inside, then we just, return some, or for an error, return something, whatever, right? It just return not found. Otherwise, then now we know that it has to be within 1 to n. And of course, it can actually appear in multiple places, but we only care about the first instance. So the first instance, we go, okay, is it on the left side? If it's on the left side, and here, to check if it's on the left side, is the same thing. You just see, given a t, where is it on the range? Where is it, And of course, because we know that this is inside this range, if it's not here, then it has to be here. Because the number just has to be in somewhere, right? And that's it. If the number is on the left side, then you just go to the left, and you know that's going left, and then maybe you go down, go left, go right, whatever, until you see a segment tree node of one element, and that is your index, and that's it. And once you do that, then that first index allows you to do the prefix sum thing and to calculate the length, and you are Gucci. And that's basically it for this one. And of course, doing it this way, because you're looking at only log n nodes, doing all of one operation of like doing this if statement check, this is going to be n log n, right? Or log n per query rather, but n log n in total. And so let's go over the code. How do I want to go over? All right, let's go over the key idea first, and we'll go over the segment tree afterwards. I mean, this part we already talked about in a lot of diagrams, right? And the idea really is just The idea here is just that, given a segment tree, we start with 0. Keep in mind that there are multiple ways of implementing this. This is just the way that I hacked together during the contest. And as you see, there's a lot of debug messages because I was having issues. So yeah, but we start at 0, right? This is supposed to be, the segment tree is supposed to keep the prefix sum. We start the current is equal to 0, okay. So current is supposed to be just like the existing prefix tree, though. As you see later, I end up changing it, so it doesn't matter. But last is last sub x shows the last index in which we see x, and then best is just whatever we return, right? And then for each number, the delta is either +1 or -1 depending on if it's odd or even. So it doesn't really matter which one is which, right? Because it's symmetric. You're looking for 0, right? So then here, if x is in last, that means that a previous number exists. Change that number to 0, right? Or the number's contribution to 0, which changes all the prefix sum afterwards, right? And that's basically what this does, right? Yeah, we update the last index, and yeah, because the segment tree already contains the prefix sum. Well, yeah, so we just get the prefix sum. Current is the prefix sum of everything to the left of the current index. So it's either 0 or it is literally what we just stored in the segment tree. And then we add the current number for the current delta. And then, I have a debug print statement, and here we are actually, that's what we're doing, right? We're searching for the current so that the subarray sum is 0, right? That's basically it. There were ways you could have written this, and maybe I could handle it without an if statement, but it wasn't deemed important enough by me, right? Which is that with current is equal to 0, remember the no set or the no array has a 0. That means that the beginning of the array is 0. So if the current is 0, then you just take the entire prefix. That's what this is for, right? Otherwise, we walk the segment tree to get the index, and then we count the number of elements from that, right? And that's it. And then of course at the end we update the index to current. So we do a range. It's a range update but of one element. Yeah, we do a range update of one element. We set it to current, and we're good because keep in mind that previously it should be 0, right? Because we only updated one at a time. And that's it for this portion, right? This is everything that we said, right? And if walk, we just get the first index, right? So if you label it first, you don't even need to know the implementation detail. The key thing noting here is that this is O of n, number of iterations, and in each iteration we do log n, and that's it, I think. Oh, and another log n, but yeah, n log n is the complexity. Now let's go over our segment tree. So I pulled my min segment tree out of the past. Excuse me, Jesus. And I just kind of add max, right? Because for this problem we want a range, as we saw. So we took the min, we took the max. I think, and you can watch the live portion and see how I alter it, because I start with the min one with the lazy propagation already written. I just added max, and here's what it sounds like, right? We just keep track of min and max. Lazy is lazy prop of adding adding x or whatever to the node. But I'm not gonna go over lazy propagation on the segment tree for this video, but this is just to build it out. And the build is actually not that interesting. We probably could have just set everything to 0, but yeah, whatever. Pull and apply, it is a lazy propagation segment tree thing. Again, I'm not going to go over it too deeply on how this works. because that's just like segment tree internals. But what I did change though to let you know is that I saw the min and I just updated the max. Pretty straightforward. Same here, right? This is applying the lazy propagation. We update the min and the max for the ranges, and then yeah, and then push again lazy propagation code. So I'm not gonna think about it or mention it. And range add also is pretty. I don't think I changed this at all for this problem. It's just adding it for a range, and this is also standard lazy propagation code, right? I mean, this walk and get, right? Yeah, I think get code is also pretty straightforward. Get is just getting it for one index, and if you have one node, then the min and the max should have one range. I added an assert to make sure that's the case. So you only have one number, so that's just getting it for a given index, right? And then the other thing is walk. So this is the only thing that is. I mean, all the other ones, all I mostly did is just to make sure that I handle min and max, or I make sure that we handle max. We already have min, but the walk is the new code that I did. There's also range min query, but I guess I just removed it because we didn't use it. Maybe it could have been handy, but whatever. But yeah, but the key thing about why we want to use this walk, which I actually skipped over a little bit, is because if you don't, like another way to do it is that you could just binary search on the prefix, right? But if you do binary search on prefix, it becomes n log square n, which maybe is too slow. I don't know for this problem. But when you could do the walk, it eliminates the log square or log square n to just log n, right? And I'm not gonna go over that. I mean, if you know what I'm talking about, you know what I'm talking about. If you already had that idea, but you just didn't do walk and you try to binary search, that's basically the idea. But the walk is basically everything that we said as well, right? We just look directly at the nodes instead of doing binary search. We go, okay, well, if this is out of range, we turn infinity for the index, which is everything to the right, so it's fine. If the query range doesn't make sense, this, I don't know why I did, maybe I shouldn't have this, I don't know. But yeah. And if this is only one node, then we just return the index, right? I mean, these are all should be the same number because there's only one node. So that's the index and that's what we're returning. Otherwise, I just want to make sure that we update. I kind of just put this in there. And that actually cost me a wrong answer because I put this here before and it gives me out of bounds. But I just want to make sure it's updated. I think you don't need to push. I think it's just to pull. But actually, now that we're not in contest, maybe I could just try it. But yeah. But the pull, just make sure that we pull the updated data. Actually, I guess it doesn't really make sense either way, huh? Because this looks at the next node, so so maybe I want push instead because we're looking. The reason why maybe I needed to push instead, and maybe we need both. I don't know. Is because we then now look at the children nodes. So maybe it's not a pull because pull pulls it to the current node. Okay, fine. Right. We push it to the children node to make sure. Yeah. Okay. So okay. But yeah. But here it should look kind of what we're talking about, right? We look at the middle and we say, well, is it on the left side? Does T, the number we're searching for, T being target, does it appear on the left side? We take the min, the max, and the node times 2 is just the left side node. Is it inside the range? If it is, then we recursively go to the left side. Otherwise, we go to the right side. And as a result, because we divide by 2 every time, this is log n, right? And that's it. That's all I have for this one. Let me know what you think. We'll show you the code together, right? So this is my segment tree. It is yeah. I mean, I have one for min, and I just took it and updated with max, and then of course I have to do the walk. And the only thing that really is like, and even the walk, I think this is pretty standard walk, even though it took me a while because I don't know, I don't have a template for it. But I mean, I understand it, so it's fine. But anyway, the only thing is just like this one, right? So it's not a big deal. And then getting it for each node again, left, right, D, right, and then longest balance, and this is the rest of the the code. And that's it. That's all I have for this one. Let me know what you think. Thanks for watching. And you could watch me solve it live in the contest now. Alright, let's take a look at today's Q4. Alright. So n is 10 to the whatever. 10 to the 5th. So we can't do the obvious thing. They have to be distinct even. What does that mean? Is there a sliding window idea? The distinct part is interesting. There's 10 to the 5th numbers, and there are a lot of numbers, so we can't abuse either of those. We have about an hour to this problem. Can we do a binary search? Don't think so. I don't think this is a binary searchable thing. It's really hard to do merge when you need to do distinct stuff. So I would say if this was a contest, then I would, that would have been very sad that I have 3 wrong on Q3. But this thing is weird. Is there another way for me to think about this thing? Is there like a... The thing is that if this is alphabet, like if this is 26, then we could do the bit mask trick. But 10 to the 5th, I don't think we could do the bit mask trick. Is there another way of... how do I think about distinctness? The hard part about this is this distinct portion, right? Because otherwise, if it's just odds and evens, it's straightforward. So then what can I think about for the distinct portion? I mean, there is like a memory that I'm thinking of, but I can't really place it. There is some like sliding window idea. Can we re-index them? Does that even matter? Okay, so without the distinct part, it is trivial. So then how do you think about the distinct part? How do you count it? Okay, go back a sec. Let's say you have this number. What if this is the last number? What is the longest band subarray that includes this? Maybe that's a contribution thing I could think about. I don't know though. I mean, I guess that one is the... Maybe I am thinking of the recent daily problem where there is a bit mask trick that I spent too long on. Maybe that's I keep on thinking about it. But then now this is not bit mask anymore. Or maybe it is, but I don't know. And that one had a constant k, I think, of number of distinct things. Just not quite the same. I mean, maybe you could solve it for all 26. Oh, I mean, at 26 you could solve all 26, but you can't really do it for this number of things either. I mean, it's nothing about odd or even. It's just groups of numbers, right? So then you think about them as +1, -1, maybe. So that's the basic idea. But I still don't know what to do without the distinctiveness. Well, distinctiveness is good in the sense that it extends the current balanced answer. Can I build something based on that? Then just kind of merge to the left and merge to the right. Okay. No, I mean, I don't know how you would do it because it depends on where the starting and ending is, right? Well, okay, let's say we start with a number or we end at a number. Then what is the longest that you can go back, right? So this is, can you binary search backwards? No. So for every number, okay, we have a segment tree. We can, no, I mean, we could just do a lookup, but then we have to, because it's not just that you have to walk the number of distinct or non-distinct things, and that would be n squared because you have just one that's like 1 2 2 2 2 2 2 2 forever, and then you would have to do some n squared stuff if you have to parse every 2, right? Then how do you do the interaction? Can we do a range subtraction in a way? Okay, so you have +1, -1. But the thing I'm trying to think about it is something like, I don't know, you have like 1, and they could all just be, and then now, so then another way is going to do this. But then it's not all, you have to handle all the dupes. And it's not just the dupes. Can you do some recursive stuff of subtracting all the numbers from the previous one? Is there, is there a segment tree that gives you the first 0? Because then now, well, not even the first 0, the first find, because you have to find the current thing, right? But then you do a subtraction on all the prefix. Subtraction. Let's see. It's not the max or the min. It's just the first instance, right? For the greedy length. Because we have to lazy add. That's the thing, right? Because we're lazy adding. It's just a well, no, it's continuous, right? So I guess that's the thing, is that it only goes up and down. Then we can do a search. Because then now you have something like the sum is going to need 1, 0, well, okay. And what would the graph be? On the search, we keep track of the min and the max. And keeping track of the min and the max works because it's +1, -1. Okay. How would I write that? All right, we have 51 minutes. We should be okay, but all right. Let me find my template for the segment tree. What is it? No, that one is not the lazy one. Right, what's the other one? Okay, this is the min lazy min tree. What do we want to change? Do I care about range min? No. I'm gonna do max, right? So we also want to do max. What is n? N is 10 to the 5th. I don't know if the constant is good enough, to be honest. But okay, so keep track of max min of the nodes, and then we just walk the tree, maybe. Okay, I could see that. Okay, this is fine. What am I doing? Just make it slightly faster. I do worry about it. Okay. I guess actually, I guess the lazy part doesn't need to be lazy min or max. It's just lazy because we, okay, a little bit less typing. This is a range add. Okay, that's fine. Pull. I actually don't need range min. Do I need range min? No, we just need to walk the tree, so we don't need to do. Let's just keep it for now. Get is fine, I suppose. Okay, I think this is good enough for me to start on. But let's say we have this, right? We have two, but then now we have this one. We actually want to, what does that, this one mean? This one means that we want to do, let's just say -1, but then now this double counts, right? So what we want to do instead is update everything from 1 back to 0, because we don't count it anymore. Is that right? Actually, I mean, it's kind of right, but it's just that now the -1 doesn't match with anything. So I thought that I can just erase the 1, treating it as, but then we want this one to match the 2. So then if the prefix is going to be, is either that or maybe we just do a range on everything afterwards. So then now it becomes 0, 1, and then now this is a 0, but then this matches this, which is not what we want. Actually, we want to match the prefix 0, but that's fine maybe because that's just the first node, right? So then now actually we want to find the last one and then increment everything afterwards. Is that right? Okay, let's do the 2. The 2, we know that there's a 2 here. We want to add, for that means that we want to subtract 1 from all these. So -1 and then 2, now we have 0. Okay, I think this is kind of on the right track. I actually thought I was going to do stuff to the prefix, but actually maybe this way is actually a little bit easier. About 44 minutes. Okay, fine. We still have to write some part of the segment tree, but we can. Is there no value? Why don't I have a value? I guess we just store it on the nodes. I guess that's fine. The get is the value. Oh. I mean, well, range min, we have to change range min, but range add is fine. The get we have to change to is range of, well, I guess if there's only one node, it's the same, so actually maybe that's fine. Okay, and then maybe we could just, for debugging, we'll do stuff later, right? We actually don't want an array yet. We want this. Right, okay. And then now, okay, for, we also keep track of the last place we've seen stuff. Right, so then now for yeah, and then now for current is equal for x index nums, right? If x mod 2 is even, then we want to plus 1, say, right? So we would check if x is in last. Then we want to increment, or we want to undo. So for example, the 2 is actually plus 1. So when we have this 2, we minus 1, right? So then now range add x to index, maybe not index minus 1. We want to minus 1. Right, and maybe we have a helper function for debug. Yeah, whatever, we'll do that for now. And then now we have, well, just add one number, so index plus 1 for even numbers, and then we just print debug, right? So okay, else and we can do some maybe the other way around, it's more synthetic. Something like that. I guess it doesn't really matter the signs. Okay, and I want this sequence as a test thing. Okay, that's too much printing, but okay. maybe this. Okay, so the 2, that's not quite right, because this should at least do some. Oh, I'm dumb. Actually, this is supposed to be delta, so you go to negative delta, and then we do this for everybody. Okay, so then now even plus 1, odd. We don't store the value of whether it's 1 or negative 1. We want the prefix sum, right? Yeah, okay. That's fine. This is not so fine. We want okay. Because then now this should be all 4 because this 0 will match the 4. This should also match all 5 because this 0 should match all 5. Okay. This one should. Oh, it's only this one. This one should do. Nope, no match. This one will match 2. This isn't quite right though. Oh, I didn't update last. Okay. Did I do it in the wrong direction? It's possible. So I have negative 1 for odd, even made it 0, okay. And then we made another odd, okay. And then we made it another 0. But then it's this thing, right? So maybe, did I do the signs wrong? I did the signs wrong. But then now, the 2, oh no, it's not supposed to match the beginning. So maybe I did the signs right. What was it? This? No. 0, 1, 2, 0, and this is good. And then here we want this to be we want to cancel it out. So then we do negative 1, negative 2, and then we have 0. But then it's 0 plus 1, and then it's the first instance. So I think that's actually right, but maybe not. Or rather, current has to be updated by the last thing, right? So let me get index minus 1. I think that's the yeah, okay. Something like this. It's very hacky looking, actually. Is that right? I mean, this looks so weird. Oh, plus delta, that's why. Okay, so it's correctly weird. Alright. Maybe. The answer is 4. That's not right for here though, right? Oh, this is actually true with delta as well. It's just that we want. Okay, I see. Okay, so then now negative 1 matches the first. This matches the first, and this matches the first. And then now for our weird case, we have this. Technically, I'm putting out all this stuff that doesn't matter, but here, this should be this one, which matches the first one, and also all the other ones technically match, which is fine, which is true. But we need the longest one. So then now we need to, okay, so I think now we have the segment tree and the data structure in a good place. All this is log n so far, so we are happy, well, except for the display. But then now, we have 35 minutes left. But now we need to do the hard part of getting the right? And we don't actually use this anyway, but oh no, we do actually end up using it because we use it for here for the prefix sum, updated prefix sum. So that's why I want to take this out. The range min doesn't matter. Okay, so how do I walk again? I guess this is actually the parameters. So walk, we want to look for, I don't know, T for target. This is from the find min, right? So then now we want to see. Okay, so we want to return the index, right? So okay, so let's just say that best is 0, 0, and then now, if current is equal to 0, then we just set it to the length because that matches the beginning. So best is equal to max best index plus 1, I think. Yeah. Else best is equal to max or f max. Let's just do best st dot walk. Man. I always forget how to call this. This is this is 1 then, right? Do we start with the node 1? Oh yeah, actually I even have it. L is 0, right is none. I'm gonna walk. Oh no. How do man? How did I forget how? I mean, it's just like 1 and n, right? But I always forget. Okay, how? All right, slow down. Okay. So we want to walk from 0 to the current index. The current index would never match by definition. Well, or by definition actually it would match. So maybe index minus 1. Node is 1, 0. Where's R again? I guess just n minus 1, I think, in the beginning. Yeah, okay. And then t, right? So, okay. And this actually gives me the index, so this is actually wrong. But, mark 0, index. Is it 0 based? I think so, but, and then we're trying to find current. Yeah, I mean, I can best index minus previous plus 1. I think that's it. Well, we have to fix this part. Okay, so we'll never be none. It's fine. Oh, I guess that's why I wrote it this way, because if you set it to this, it actually messes up. But okay, fine. Okay, so then now, yeah, and it's fine. Okay, fine, because this gives me an infinity index. Otherwise, then now, where's this? If if this is inside a range, then we do this. That's not what we want. What we want is to walk the first index. Okay, so this is just not right. Oh, this is for a different problem. Then now we just have to do the left edge, right? So mid is so that means maybe I do need the min thing. No, because then that is that a I'm just looking at this and it looks very weird. Oh, this is the query, that's why. And then so okay, so then that means that the left side is it's been a while since sec3, that's why. So then does t appear on the left side, and then so then now if t is between self.min v of node times 2 max v of I guess there should be another thing first, which is that if self.min v of node, if t is less than this or t is greater than self.max v of node, then we return infinity. I don't know why I don't know, it's not inconsistent. I don't remember when I wrote it. Okay, so then now does t appear on the left side? So if this is on the left side, then we walk left, right? Return walk do I change the query? We want the first index. Okay, no, I mean we have to change the query, but that's fine. Else we return self.walk. It's been a while since I did the walk thing, that's why I'm like a little bit shaky. But you basically have to do the min on this, right? So then now the mid is going to be f min of query mid, right? And this is f max. Is it max? Yeah, okay, of mid plus 1. I think that should be good. And that should give me the index. No, I mean, well, yes, but I don't have a base case. It doesn't even have a base case. So, okay, so then now, if ql is equal to qr, then we have exactly one thing left, and it's within is t, and t is inside. It shouldn't be assert t is equal to return index. What is the index? It's gonna be L is equal to R, right? I think so. Could be wrong. Non-default argument. Oh yeah, T. I mean, it's fine. We always have an argument. I think. I always have an argument. I mean, I lied because I forgot to pass T, but. Okay. 4, 5. Oh, I have 4 here. I mean, these numbers are also just not right? So, Wait, where am I pointing? Where do I point? Oh, I put the index, and I always put index as 0. That's maybe not right. Why is query left and query right? Okay, so we're looking for T, so I mean that's fine. But L and R, is this not right? Am I missing something? Mid plus 1. I don't know what I'm looking at, so maybe that's 10 is probably actually right for, I don't know, 10 is actually right, but this is, what would I return? I returned 4, and it should be 3. Why? Did I mess this up? Alright, let's see. Let's bring this back in. Maybe take this print statements back out. Okay, well, this. Something's weird. What is this? No, so this is definitely a thing, but we only add +1 or -1 to. So it cannot go to zeros. That doesn't really make sense. Right? Neither does this really. Oh no, this is another print. Okay, so I have another print statement, that's all. That's why I'm confusing myself. Oh yeah, okay. I see. Alright, let's just keep that focus. Okay, 1. So the first instance should be 0, right? 3. Oh, this is not inclusive. Because that's the last time you see that number, so it's not inclusive. Okay. Alright. Am I confident about this? Honestly, not at all. But we have 23 minutes. Wow, actually took quite a while. We have 23 minutes. Let's YOLO submit real quick. I mean, I've already YOLO submit a lot on the Q3, so there also may be some timeout issues, but we'll worry about it when we get there. I hope it doesn't time out though, because this is so close. Why would it give me 1? Also, that's actually sad. -1. We're searching for current, right? So, okay. Why is it giving me 1? Oh, because this might return nothing. No, I thought it would return infinity. Searching for -2. Let's see, what's my base cases? So it's not finding it. This is finding. Okay, this is infinity, but this is finding 0 for -2. Why? We update this, right? Oh, on the walk we might have to. On the walk we might have to push. I forgot. Okay, that's fine. Why? Okay, well, why is it not going out of bounds? Why? It's pushed only. Oh, is it push or pull? Why that? Oh, maybe it's pull. Well, maybe it's push and pull. I don't know anymore. Okay, let's see, YOLO. Nope, still no good. Pushing and pulling. Why? What's the range? Why would there be a -2 in there? We don't have. Okay, so we're searching for -1 inside index -1, right? So we should not match itself, which is what 1 would mean. 1 would never be the answer. 19 minutes, so we're cutting it close. Did I do something weird with this? X-Men. Is this right? I think this should be right. Oh no, mid is, because all is always n-1, so mid. No. This is. No, I mean, this is. What we want is not on the entire tree. What we want is on. How do I only look at this part of it? Well, I guess I can also just update it afterwards. What am I doing? Because this is the only place where it could be bad. So okay, maybe I don't know how to do it quite off my head right now. Okay, so that looks good. Just have to. There's definitely a way to do it, but I'm like blanking out. All right, YOLO. What? This is an earlier thing. So what did I change again? I change updating this. Why does this matter? Oh wait, do I update index or something weird? No, index current. Huh? How did I change other code? Oh, I guess I added these. Does it still work? Bring it back. Yeah, I mean, but we definitely still need to push and pull, just not here, maybe. Maybe here. I don't know. Let's use. Did I use this one already? I did. 16 minutes. So many wrong answers, and it might still not be fast enough. But if it's not, actually, let me just ask. Let's convert it to Java if it's fast enough. Oh, actually, it's accepted. Okay, so I don't. This is a hard problem. 120. Is that like? I think like 120 people solved it, so I'm literally like the last. But I got 5 wrong answers, so it's not that surprising, right? Because 138 is longer than all the contest time. So yeah, I'm happy. I'm happy that I solved it. It is a very hard part. I enjoyed it though, to be frank. Right, I'm just putting it in my thing. I'm just looking at the end. I'm not gonna lie. I'm cheating right now. I'm looking at my Discord, see how people did Q4. Seems like pretty straightforward. I mean, I see that people did square root decomposition. I don't know how you do them. I guess you could do the merge. Maybe that's fair. I don't know. I mean, all this is a little bit hard, to be honest. I mean, obviously, I think this is definitely not an easy problem. But yeah, all right, let's do a quick retro. Sorry, I'm just catching my breath because this is a mess, and I really should handle this. Actually, let me. I don't know. I don't know enough about segment tree. Because what I want is not to walk the entire tree, but walk the prefix of a tree. I don't know that I know how to do that. Because node is an implicit thing on this. Right? I mean, I guess you can. You can just keep walking until you walk the prefix. And you have to find the node that correspond to it. But it's just a lot more work around here. And I just didn't... I'm not confident about getting it quite right. Well, I guess I can build off the prefix. The idea that we know that this is doing prefix. QL is always 1 or 0. So then it is just about this. And then that we can just keep walking to the... We can walk in a more direct way. I guess that's how you would do it. But that's still like a very... obviously a hard problem. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.